Okay, so today we're going to do the principle of increasing entropy of the universe. Okay, so the title sounds pretty complicated. So let's see. So principle means that it's derived from a law or from one equation. Increasing means that it goes up. Entropy, we haven't defined it. And universe, basically, we know what that is. So from the previous video, we derived the Clausius inequality or the theorem that basically stated that delta Q over T is equal or lower than 0. So if this ratio here was equal to 0, we say the process was reversible. And if it was lower than 0, we say it was irreversible. Okay, so now this is the part which is a little bit complicated to understand, the principle. So let us first define what is the entropy. So the entropy mathematically is defined as delta Q over T from this equation here, okay? The ratio delta Q over T is defined as the change in entropy. So let's say S final minus S initial equal to delta S, where S over here is the change in entropy. So basically, if you need to look at the units for this, what should be the units? It would be joules per degree Kelvin. Johnny will be kilojoules. Okay? Alright, so what is entropy? Probably you heard very complicated definitions based on if it's related to the stability of the system and so on and so on. But let me just give a very simple definition. So first, entropy means in Greek transformability. So for me, the easiest definition for it is the entropy is a measure on how well the energy is utilized in a process. So basically, what does that mean? If it's equal to 0, it's reversible. So what does that mean? If delta S is equal to 0, that means that we did not waste any energy. So basically, the energy we have at the beginning, we have it at the end. So this will mean that this is reversible. Okay? Now, I'm going to do a derivation, but I think it's easier just to understand it on a sentence. It's kind of easy to understand or to believe that any process is not perfect and is going to lose energy. Okay, it's going to lose energy, so the entropy will not be equal to 0. If it's not equal to 0, it will actually be positive. It will be delta S will be equal to the amount of energy that is wasted that we cannot recover from the process. So every time there's a process happening in the universe, that entropy of the universe keeps increasing, increasing, and increasing. Okay? So if you want, I'm just going to do a quick derivation now to show you how generally this is done in textbook. But I think this sentence is easier to understand. So probably you will find in many textbooks that if you have, so this could be P or TV, okay? So let's say we have a process between points 1 and 2, and we're going to go from here first and then here, and this one here we're going to say is reversible, internally reversible. Okay, so we go through this process in both of them. What do we have? So we have the general equation, delta Q over T. So this is from the Clausius theorem. This will give us what? So we first go from, maybe I should remove this one, but so in here we first go from 1 to 2. This is the general process, delta Q over T, plus 2 to 1 from here to here. So we went from here to here, and now we go from here to here, delta Q over T for the reversible. Okay, but we know that for the reversible this will be equal to the change in entropy, so it would be in this case S1 minus S2. So if I go to the next page, okay, let me just rewrite the last. We have 1 to 2 delta Q over T plus 2 to 1 delta Q over T reversible. And this should be lower or equal than 0. Okay, so we recognize over here that the first one remains unchanged, plus this will be final, so S1 minus S2, and this should be equal to lower than 0. Okay, and I can just rewrite this as S1 minus S2 delta Q over T, or S1 minus S2. So I reverse the sign on this side. So that means we reverse the order of the inequality sign, delta Q over T. So this will mean that all this term over here is delta S will be higher or equal to interval of delta Q over T. Let's say we integrate. So if we integrate, we're going to have ds on this side should be higher or equal than delta Q over T, which is our entropy. So basically the only thing I'm trying to solve here is that initially from the definition of the Clausius theorem, a process is reversible if it's equal to 0, if it is irreversible if it's lower than 0. But once we introduce the principle of the increase in entropy of the universe, and it's due to this equation, you see that the entropy is always supposed to increase. So what happened at the end is that we can write down that the change of entropy of the universe will be equal to the change of entropy of the system plus the change of entropy of the surrounding, okay? Or just delta S universe equal to change of energy of the system plus the change of energy with the surrounding. And in most cases, the change of entropy of the universe is equal to the change of entropy of the system, and the one of the surrounding will always be of the form delta Q over T of the surrounding. So let's try to understand this term a little bit with a figure. So let's say you have a system. This can be a closed or open system. All right? If the heat is going in, we know this is positive. If the heat is going out, we know this is negative. So what does that mean? If there is heat going inside the system, it will increase the entropy. Okay? And let's say this will be the temperature of the surrounding. Okay? However, if it's leaving, it will be decreasing the entropy. That's why one definition of the entropy is what? If you put more energy into the system, you increase the entropy. If you increase the energy inside your system, you increase the, if you want, the heat and the collision between all the different molecules within the system, so it makes the system more chaotic. Okay? But again, I think the easiest definition for entropy is just a measure on how well you utilize the energy. So when it's zero, basically you will say that you optimize the energy because you didn't lose anyone. But if it's not zero, basically it's positive, you will say that you lost that energy. So with that definition, and I will finish with that, we'll have that if delta S of the universe is zero, the system will be reversible. If the energy of the universe is higher than zero, will be irreversible. And if it is negative, okay, we'll say that it will be impossible. Okay, thank you very much, and I try to keep this as simple as possible. Okay, thank you for your attention.